In this video, we're going to focus on aldehydes and ketones. As we learned in the previous chapter, when it comes to aldehydes and ketones, these functional groups are going to be characterized by the presence of a carbon double bonded with oxygen. That carbon double bonded with oxygen is known as a carbonyl group. When it comes to aldehydes and ketones, the difference structurally for these molecules is that aldehydes specifically, the carbonyl group is connected to a hydrogen, while in ketones, the carbonyl group is connected on either side to carbon chains. In the bottom of the slide, we have the structural examples of the smallest aldehydes and ketone respectively. When we look at this left side, we can observe that methanol is going to be the smallest aldehyde. We can observe that there's only one carbon atom, and on either side, we have hydrogens. Methanol is known more commonly as formaldehyde, and formaldehyde is a compound utilized in the preservation of animal specimens. On the right side, we have the smallest ketone. And the smallest ketone, which has 3 carbons in length, it is known as propanone, and propanone, its common name is acetone, as you can see in the container. Acetone is a very common solvent in organic chemistry. You can also in this slide see how specifically we write the condensed structure for an aldehyde, the skeletal structure for an aldehyde, the condensed structure for ketones, and the skeletal form of a ketone. Now let's proceed to learn how to name these two functional groups. When it comes to naming aldehydes, let's understand that the steps are, you're going to find the longest carbon chain that contains the CHO group. The CHO group is going to be the C double bond OH. You're going to write the alkane name for that parent chain, and then the ending of that parent chain, the E will be replaced by the ending AL for aldehyde. You're going to number the chain, counting the carbonyl as carbon 1, and this is only going to be present for straight chain aldehydes. We're going to see in the bottom examples how we treat aromatic aldehydes. And then we have to give the location and the name of the substituents as a prefix of the name of the aldehyde parent chain. Please do not forget to put hyphens between numbers and letters. So here we have actually 2 examples of aldehydes. Let's first detect in this molecule what is the longest continuous carbon chain present. So overall, I hope that you found that the longest carbon chain is this one, 5 carbons in length. Because if you go this way, or if you go that way, it's only 4 carbons in length. So this is my parent chain. When I'm number the carbons in an aldehyde, the carbon in the carbonyl for the aldehyde is always carbon 1. So you in aldehydes don't need to put 1 and then the parent chain because it will be redundant. A 5-carbon aldehyde is called pentanal. If I number the carbon atoms in my parent chain, I can observe that I have specifically a substituent that is 3 carbons in length. 1, 2, 3. And since the connection to the parent chain is through the middle carbon, that is an isopropyl group. So for this molecule, the complete name will be 2-isopropyl pentanal. Remember that I don't have to put the 1-pentanal because carbon number 1 is always the carbon in the carbonyl in an aldehyde. When it comes to aromatic aldehydes, the numbering of the carbon chain is a little bit different. Similar to what we observed with the phenol group, the benzene ring connected to the CHO group is going to be our parent chain. Let me highlight it. So all of these atoms that I'm highlighting in yellow is my parent chain. A benzene ring connected to a CHO group that is known as benzaldehyde. In this molecule, I must, if present in the ring system, a substituent, I must number them with the lowest number possible. You can go clockwise or counterclockwise. So instead of numbering the carbon in the carbonyl as carbon 1, for aromatic aldehydes, the carbon that is holding the CHO group is carbon number 1. For this particular example, we have carbon 2, carbon 3, carbon 4, 5, and 6. On carbon 3, we have a substituent. This substituent has 2 carbon atoms. So that means that that is called an ethyl group. Its position is number 3. So the name of this structure is 3-ethyl benzaldehyde. Let's now proceed to name ketones. When it comes to ketones, we can observe on the left side of the slide that the rules are that you're going to name the longest carbon chain by replacing the E in the alkane name by the ending ONE. In other words, own. Then you're going to number the carbon atoms starting from the end that is closest to the C double bond O in the ketone. We're going to give the location and name of the substituents as a prefix of the parent chain, but let's not forget that we need to give specifically if we have 5 carbon atoms or more in our ketone, where's the position of the double bond oxygen. So let's do the problems that we have on the slides. Take a moment and find what is the longest carbon chain of carbon atoms in this ketone. Starting from this end, which is the one that is closest to the C double bond, this carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. You could have also selected 1, 2, 3, 4, 5. It will give you the same name. Since we have 5 carbons in our parent chain for our ketone. Let me highlight them. The alkane name is pentane for 5 carbons in a row. But because this is a ketone, I take the E and I replace it by O-N-E. So that is pentanone. Since my straight chain ketone has 5 carbons, I need to put what is the place where the double bond O is. It is at position 2. I only have one substituent in this molecule, which is at carbon 4. I have a methyl group. The name of this structure is 4-methyl-2-pentanone. Don't forget the punctuation when it comes to structure. Every time we have numbers and letters, we must separate them by a hyphen. Ketones can be cyclic. And as we can observe in the following example, in a cyclic ketone, we must determine how many carbon atoms are in the cyclic system. In this cyclic system, we have 1 carbon, 2, 3, 4, 5, 6. We name the cyclic system, which this is cyclohexane, but because it is a ketone, then this is cyclohexanone. When it comes to numbering a cyclic ketone, carbon number 1 is going to be the one that is double bonded to oxygen. So in this molecule, this is 1. Then you have to number the carbon atoms within the ring system to the lowest possible number for the substituents. So this is carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. We have one substituent in this molecule. Let me just move the name down here. Since we only have one substituent, and that substituent has 2 carbon atoms, the name of this ketone is 4-ethyl cyclohexanone. Let's now practice how to name structures for aldehydes and ketones. I'm going to specifically do the 2 that are in the middle when you look at the whole slide, but in this zoomed in version is going to be the ones on the left. On the molecule on top, since I have a benzene ring connected to a CH group, that is my parent chain, and that is called benzaldehyde. In this molecule, I must number 1, 2, 3, 4, 5, 6 in order to give that substituent the lowest number. My substituent is on position 4, so this is 4-methyl benzaldehyde. Let's go to the bottom molecule where we have a cyclic ketone. And in that cyclic ketone, I can see that there is 1, 2, 3, 4, 5 carbon atoms. So this is cyclopentanone. Carbon number 1 is the carbon that is holding the double bond O. And in this molecule, I have to go counterclockwise. 2, 3, 4, 5 to give the substituent the lowest number. The carbon number 2, I have a methyl group. So the correct name for the following molecule is 2-methyl cyclopentanone. It is important that you know how to draw aldehydes and ketones. For this, I'm only going to do the skeletal structures for the examples that we have here. In the first one, we have 2-chlorobutanol. And in the second example, I have 2-methyl-3-heptanone. For the 2-chlorobutanol, since the name has bute in it, that means that that's the longest parent chain. And since the prefix is bute, that means that there's 4 carbons. 1, 2, 3, 4. Now, it is your artistic expression if you want to put the C double bond O on this carbon or on this carbon. I prefer to do left to right just because that's how we read in English. So if carbon number 1 is double bonded to oxygen, single bonded to hydrogen, that is carbon number 1 in that butanol. And I can verify that I did it correctly because I have 1, 2, 3, 4 carbon atoms. Next, if this is carbon number 1, then this is carbon number 2. And I'm going to write a chlorine. The next example is 2-methyl-3-heptanone. In the heptanone, that hepta tells me the longest continuous chain of carbon atoms, which for this molecule, since it's hepta, it is 7. So I write 1, 2, 3, 4, 5, 6, 7. Specifically on carbon number 3 is where I have my double bond O. That's what this number means. So on carbon number 3, I'm going to do double bond oxygen. And then on carbon number 2 specifically, we're going to put a methyl group. And those are the structures for the aldehyde and ketone that we have in the example. Make sure that you practice. The last thing that I want to mention is what is the solubility of aldehydes and ketones, specifically in water? Well, because the carbon oxygen double bond present in aldehydes and ketones is a polar bond, let's see what is the main interaction that they have with water. We can see on the right side of the slide that hydrogen bonds are going to be the main way in which aldehydes and ketones interact with water. Now, there is a limitation when it comes to these interactions. Even though hydrogen bondings will be forming between the oxygen in the carbonyl and the atoms in the water, let's understand that the limit for solubility, specifically for aldehydes and ketones, is going to be 4 carbon atoms. What does that mean? That aldehydes and ketones that have 4 carbon atoms or less are the only ones that are soluble in water. 5 carbons or more ketones are not soluble in water.